why waste our time into all that work about f of x plus delta x minus f of x all over delta x, do the math, then plug in 0 for all delta x's so we can take the limit if it's not possible in the first place. So let's take a look at some of these examples. So we need to talk about when a derivative does not exist. So first of all, we need to realize that a derivative, remember, came from limits. So the definition of derivative, again, was the limit as we approach a number. Okay? So I want you to look at this little graph here. So it's a absolute value graph. Notice it has a sharp turn here. So the definition of derivative was found by taking the limit as delta x approached a number. And then when we finished with that, we called that our slope. But if you look at the left side here, our slope is negative, and the right side, the slope is positive. So there's no way we can have a negative slope and a positive slope at the same time. And so we will often say that a derivative doesn't exist at a sharp turn. Clearly, you're going, and you're hitting a spot, and you're sharp turning it the other direction. Okay, now in this one, it doesn't look so much like a sharp turn, but we call this a cusp because it's more curvy, boom, and then curve out. So even though these are curved, I would still call this somewhat of a sharp turn. So in this one, we've got positive slopes, and it almost looks like this is a vertical line. I mean, because it's going up pretty steeply and then it curves out again. So in this case, our derivative does not exist. In this one, we would say that the derivative does not exist. One big main reason is because of the discontinuity. You can't have a gap and think you're going to find a derivative at that point. So a lot of times when we think about these weird situations where we're not sure if a derivative can be found, it kind of goes along with the fact that the left side derivative is not going to come close to the right side derivative. Kind of like limit, but not exactly. So let's apply what we know now. So it says if f has a derivative at a particular point, then f must be continuous at that point. Okay, this if-then statement does not flip back. It's not an if and only if. So it's saying if a derivative exists, we are guaranteeing that there's continuity at that point. We're not saying it the other way around. We're not saying if something's continuous, you're going to have a derivative. Okay, we're saying this is the other way around. If the derivative exists, then automatically we must have a continuous function. Okay, this makes sense because if we do in fact get a derivative, there can't be any gaps or holes, right? So first of all, let's take a look at all these x values. And usually what we're going to be doing with all these functions is when something in the graph changes direction, something's going on. So at this point, notice how our derivative would be negative. The derivative would be negative because our slope is going downward. And then it switched to a positive, right? So at this point, because of that sharp turn, no derivative. So it says describe the x values at which f is differentiable. Differentiable means that a derivative exists. So this would not be a spot that we want to write down because the derivative is not possible here. Okay, so here my slope is positive and then it turns negative. Is that a sharp turn? So my derivative can be found at this particular point. My derivative would be right here. Tangent line is right here going through that point. It's a hump. Okay? So derivatives at humps are always 0. So I'm going to say at x equals 0, the derivative can be found. All right? And I'm going to get into some intervals in a little bit. All right, so now I have a negative slope, and then it hits a point, and then it juts up the other way, and now I have a positive slope. So I'm switching direction here. What's going on? Well, it's a sharp turn. So it cannot be found here. So give me all the x values, not just these individual points. All the x values where the derivative exists, or we say that it's differentiable. From negative infinity up to negative 3. But remember, it's not found right here. And then we can find the derivative from negative 3 all the way up to positive 3. Not found right at 3, though. And then we can find the derivative again, 3 on to infinity. So we can, this is saying that we can find the derivative at any spot in this picture except at negative 3 and except at 3. So this would be my complete interval. All right, let's take a look at this. We can find the derivative here, here, here. I can figure out slopes of tangent lines. And then all of a sudden I jump over to here. I can find the slope. And it jumps over this asymptote. Okay, so where am I not allowed to find the derivative? Right here at negative 2, and then again here at 2. So I write it this way. I can find the derivative from negative infinity to negative 2. And then again from negative 2 to positive 2. And then again from positive 2 all the way up to infinity. Remember, we're looking at x values only. All right, so can I find the derivative here? Can I find the slope here? Sure. And then all of a sudden, boom, it stops. And then the function picks up again here. I can find the derivative here, 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 forever. So I'm allowed to find the derivative from negative infinity to 1. And then again from 1 to infinity. The reason I have to write these separately is because at 1, something's going on. I can't find the actual derivative right at the x value of 1. It's impossible because there's a gap. So I can find it anywhere from here to here, and then again from here to here. This kind of looks like a 6, infinity.